given by Yevgeniy Dodis.
Thank you. Thanks also. Thanks also for to the organizers for inviting me. So I'll be talking about overcoming weak expectations. So there is some pun intended here. So the expectation indeed would be weak, but we will be literally analyzing some weak expectations. But first, I guess, to connect it, at least artificially, to the point of the workshop where we are trying to kind of maybe connect the best, take the best from the two, pretty different communities, people working in formal methods and people working in cryptography. So not trying to create any controversy, I'm on tape here. But we have to come up with kind of two stereotypes, maybe that one positive, one negative, that come up when we discuss formal methods. You can kind of say, well, this is kind of very neat area, everything is precise, there is generally little controversy, you really prove everything, if you prove everything, it's people hope it's kind of correct, and it's you typically follow pedantic rules, trying to be very, very safe. On the other hand, kind of not trying to be negative, but you can say, well, somebody else invented some stupid proof, and we have to read somebody's proof or somebody's code, or it's kind of you have to follow these pedantic steps. So you can kind of argue that maybe to some extent this is boring. In contrast, if you talk about kind of cryptography, you have a completely kind of opposite picture to some extent, that especially when people kind of start in cryptography, there is security parameter, uniform attackers, non-uniform, all these assumptions, knowledge of exponent, black box, non-black box. It's just kind of people, especially initially, get really overwhelmed. So it's kind of, you can say that to some extent it's messy, but also maybe kind of the opposite thing. It's kind of, it makes it really fun. There are all these exciting things. So all this, every paper is very different. Everybody has a different style of proving things and so on. So it's kind of the fun area. And of course, in both areas, formal maths and cryptography, ideally we would like to kind of get the best. We would like to do something which is neat and also hopefully still remains fun. And this is what. So hopefully you will kind of take the best of those two fields and get like kind of this guy. Who is kind of, I guess, very fun, but and I will try to kind of follow this ambitious challenge to try to to do something which is on the one hand very kind of precise, very simple, very pedantic, but hopefully is fun and leads to some very surprising conclusions. And the area where I will try to take on this ambitious challenge is the question of how to deal with weak sources or imperfect secrets. So abstractly, the setting that I'm going to consider is you have some cryptographic application P, and ideally you would like to have a truly secret. Yes, I have to use the stick, it's pretty cool. So it has this truly secret secret key R, m-bit strings, but in reality, unfortunately, very often we have some kind of source of randomness X, but it's not truly perfect, from which we need to derive our secret. And there are many, many examples, and many of them were mentioned in the talks. Obviously, in practice, when we need to extract randoms, we take some physical sources. If we want to use biometrics, maybe for security, again, secrets are not going to be perfectly uniform. Leakage resilient cryptography, there were a lot of talks even in this workshop, but exciting area where even if the secret is originally uniform, after there is some side channel or some kind of leakage about the secret, it no longer looks uniform to the attacker. And even pragmatic settings like, we talked about TLS, but like variants of Diffie-Hellman key exchange. So fine, you get this random group element or pseudo-random group element that looks like random, but especially for elliptic curves, we understand too little about those groups. So we still want to convert it to like a key for AES. So we still need to kind of deal with some kind of weird distributions, even uniform, but on some weird domains. So there are kind of three options how to deal with these things. So the first option is to be clever and to take those things at the design time and really start to design some very particular cryptographic schemes which tolerate weak randomness. And I'm guilty also of trying to be clever in some cases, but this is not going to be the point of this talk. So here I'm trying to be neat and pedantic and not be clever. So we are not going to try to design schemes which tolerate leakage from the beginning. Instead, we'll follow the other two approaches. So the second approach is kind of, the second scenario is kind of trying to be very modular. It says, okay, you know what, I have this, somebody designs an application, they don't worry about imperfect secrets, they just assume everything is uniform. This is a setting that you'll consider, but instead I will construct a very careful key derivation function, like in Diffie-Hellman key exchange or something, such that I'm hoping that h of x is good for my application. And ideally, the best case scenario, I don't want to know anything about p, but as we'll see, sometimes knowing very little about p can help. But still, we would like to really not to go into this clever approach, but under some minimal assumptions on p, get some surprising conclusions. And the final approach is a dumb approach, where you just say, okay, you know what, let's just use our source of randomness the way it is. Essentially, the key derivation function is identity, and just hope for the best, even though our application was really not designed to work with imperfect randomness. Let's just hope, praise that everything is going to be fine. And of course, that's the setting that we're going to start. We'll try to be dumb and see how bad things are. And surprisingly, things will not be in some settings as bad as they would appear. As I said, I promised to be like very neat and pedantic, so let's start. So let's fix any application. Let's start to be very general. So we fix some application P and any legal attacker A. So they're like from now on fixed, signature, encryption, I don't really care. And now for every particular secret key R, so it's like lowercase r, so it's a very particular setting of R, we can define this function f of R, which is advantage of A on key R with respect to advantage is some application specific thing, probability of forging signature, or advantage over guessing, or something like that. And the only thing which will be important is essentially the range of this function. So for predictability applications, the advantage is usually the probability the attacker like forging a signature or something, or inverting one-way function. So the f of R will be a real number between 0 and 1. For indistinguishability applications, we subtract a half because it's always easy to guess. So essentially the range of this function is, unfortunately, could be negative, so it's from minus a half to a half. So that's as far as we need to know anything about applications. And the way we define ideal security is just by expectation. We assume we have a truly uniform key. It's essentially expected value of this function f on the uniform distribution. So u sub m is going to be uniform distribution, which is simply this kind of average, something very, very general. And of course, real advantage, whatever is our real distribution capital R, I don't know, there is some distribution P sub R, it's essentially what happens to be what is expected value of this function f on this, weird distributions that we have in reality, okay? And our goal is to, assuming some decent bound on the ideal advantage of A, prove some bound on the, hopefully decent bound under the real advantage of A, right? And of course, at this level, generality is completely hopeless. If, the attacker knows our secret key is always 0, there is nothing probably we can do in this case. But, if R has entropy, and the right notion of entropy is mean entropy, as I'll define in a second, hopefully we might be able to do something. So, and indeed, let's start. Let's start with a simple inequality. So first, let me just try to, for those of you who haven't seen it, so the mean entropy of a random variable R, will say it's at least V, if no outcome happens probability more than 2 to the minus V. So that's a standard thing. So let's look at the simple inequality. So if f is non-negative, essentially it's a completely general inequality, then we say that expected value of f of R, I can drop the absolute values, is at most, I'll explain what d is, at most 2 to the d times the expected value of f, where what is d? Essentially, it will be more convenient to parameterize the mean entropy of R as m full entropy minus something. So this d throughout this talk, as we'll see, it's more convenient to write it this way because our bounds will be kind of depend on d in a more natural way. So we'll call it the entropy deficiency of our key. So it's in some way, it's a particular measure of closeness to uniform, how close it is to uniform. And so then this bound is like that, and the proof is one line. It's completely elementary. You just write this, this is by definition, and you just take the maximum out. It's at most the maximum times this, done, right? So hopefully pretty elementary, so nothing deep. So as a corollary, we get, pretty general corollary that if you have any t epsilon, so t is like resources, in Uly's notation, constructive resources of the attacker. I don't care what it is, running time or whatever. But if you have any t epsilon secure and predictability application t in the ideal model, then it's t epsilon prime secure in the, I'll say, m minus d real model, means that the mean entropy of the key is m minus d, where epsilon prime, I'm sorry for this bad yellow, but epsilon prime is at most 2 to the d times epsilon prime. Which, you can say, yeah, it's exponential loss, but, it's not so bad, actually, in some sense. You can see that this is tight in general. And, just I don't want to dwell on, but like, for example, a simple example, for example, if we have a one-time MAC, AM plus B, it's well known to be information theoretically one-time ACK, where the ideal security is 2 to the minus m over 2, where m is the length of our secret key. In this case, our secret key is A and B. So here from this lemma, we can completely generically, for example, rederive, pretty simple result of, for example, Uli and Stefan Wolf, that this MAC is also secure with respect to these keys with this kind of security degradation. And of course, that thing is like very easy to prove directly, and indeed, Uli and Stefan prove it directly. But our point is it's like something completely general. So this kind of statements, when you want to talk about unpredictability applications with weak keys, you can immediately derive these generic bounds without reproving them from scratch. All right, so this was simple, pretty elementary. All right, so let's try to talk about indistinguishability applications. So what's the problem with indistinguishability applications? Well, remember, this bound is only for f non-negative. So we want to kind of derive things, some inequality even if f is negative. So in this case, it will be slightly more convenient. We'll see why to derive yet another, I promise, the last notion of entropy in this talk, which is the Renyi entropy or the collision entropy, which is essentially log of the collision probability. So what is the collision probability of distribution R? It's the probability if you sample two independent samples of R, R1 and R2, what is the probability that they collide, which is sum of PR square. And the Renyi entropy is minus log of this. And it's very easy to see that this is, that it's lower bounded by mean entropy. So in particular, if I have a lower bound on mean entropy, I will automatically have lower bound of Renyi entropy. So I didn't have to, so let me actually put the inequality in a second here. So for this inequality, I could deal with mean entropy, but as we'll see, it's easier to ensure a good bound on Renyi entropy. So I will put it on this level of generality. So here is again a completely general thing that for all functions f, the expected value of f is at most, I pay the square root, is at most square root of 2 to the d over times square root of expected value of f of f square on the uniform distribution. And again, what's the proof of this thing? It's pretty elementary. Just write the definition. This is sum of p of r, f of r, and of course, when you see sum of ai b sub I, you know what to do. You should apply Cauchy-Schwarz. So kind of when I was a kid, I always wanted to apply Cauchy-Schwarz in one of my papers. So eventually, I did it. Pretty elementary. So you just apply Cauchy-Schwarz, you get this and this. So the red term is essentially exactly the collision probability times 2 to the m. You'll get 2 to the d, and this is by definition expected value of f under uniform distribution done. All right. So this is pretty elementary. So all right. So why is it nice? Why is this kind of a nice inequality? Right. This guy is enjoying it. So look, it works. First of all, it works even if f of r is negative. But also there is a separation of two terms. So the first term is it only depends on mean entropy of r. We don't need to know anything about the application, right? Where the f kind of tells us something about the application. And the second term is for uniform distribution. So we got rid of our difficulty of analyzing something with respect to weak sources, right? So it's completely, we can kind of separate it. But now, of course, you can ask the question, okay, this 2 to the d, we understand it's the entropy deficiency of our source. Expected value of f, we define it, it's epsilon, it's our security of our application. What is expected value of f squared? What does it really mean for the application? I don't know what it means, so let's just give it a definition, let's give it a name. We'll say that, I promise to be very pedantic, so far I follow it, but hopefully very soon, hopefully we'll see some surprises, not yet. So let's just define it. We'll say that P is T sigma secure if any T-bounded attacker of A expected value of the square of the advantage of the attacker is at most sigma. All right. So I just define it. So now, so what is this square security? So now we can first of all immediately get the following corollary. The corollary is that if our application is T sigma square secure, then automatically in the ideal model, then in the real model, it will automatically be square root of sigma times 2 to the d secure, completely generically. All right, that's good. And to some extent, if you care about weak randomness, it motivates the study of square security. But of course, we, rather than just making some weird assumptions that AES is, 2 to the minus 126 square secure or something like that, you would like to really understand, hopefully related to the regional security, because we spent a lot of time analyzing a regional security epsilon of application. So how does sigma relate to epsilon, right? And the trivial thing, unfortunately, goes in the wrong direction. But Jensen inequality tells us that epsilon sigma is greater than epsilon square. Expectation of the square is greater than square of expectation. well, this is a fantastic bounty if we get it, because then we'll get epsilon. Is it tight? Well, unfortunately, no. It's very easy to see that this is just too good to be true. Nevertheless, I'll show you that for a wide variety of cases, we can actually prove that sigma is approximately epsilon. So let's try with, let's start with some predictability applications right away. We already had lemma 1, which dealt with some predictability application, but let's get like another way to do it. So the observation is from predictability applications, because f is non-negative, I claim that it's, look, what is sigma? It's expected value of f squared. And a negative variable square is at most, you know, f, right? So numbers between 0 and 1, you square them, they only become smaller. So it's at most expected value of m, which is epsilon. And that's, again, it's very critical that this cannot be, you know, negative. But here, automatically, we get the foreign corollary. So if you have any unpredictability applications, then we get essentially this kind of bound. And for a second, you can say, wait a second, we just proved a much better bound epsilon times 2 to the d, and here we just pay square root, which makes the bound worse, right? So this is kind of bad. So far, this exercise led to a bound, but the bound is much worse than what we could get directly from predictability applications. So I want us to stay tuned. So for now, it is true. This bound is not very useful from predictability applications, but we will see that it will be useful from predictability applications when we go from the dumb approach to the modular approach. But for now, let's just keep it in mind. All right, so things are kind of bad for now. So let's go from bad to worse. Let's try to analyze the square security of the one-time pad, right? Everybody knows what a one-time pad. Well, the first thing is a sanity check. We expect something should go really wrong for the one-time pad. Because even if the entropy of the key is m minus 1, even if only one bit of the key is fixed, we know that one-time pad is insecure because you learn one bit of the message. So presumably it should translate somewhere in the bound, and indeed it will, because let's look at the one-bit one-time pad. Just everything is just one bit. So consider the following attacker who just copies, he gets a challenge ciphertext, and he just says, I guess that the message is equal to the ciphertext. Well, if the key is 0, the guy is always right. The message is equal to the ciphertext, right? Because it's plus 0. So his advantage over guessing is a half. If the key is 1, the guy is always wrong. So the advantage is minus a half. Epsilon is still 0, expected value of, you know, 1/2 minus a half is 0. But once you square it, you get 1/4. So you get application with really horrible square security and great perfect security. But in some sense, it's a good. I view it as a sanity check because, yeah, we don't expect to get a good bound for the one-time pad. And unfortunately, that's more unfortunate. Similar problems happen for pseudorandom generators, PRFs, and PRPs. Even though for those of you who came to Krzysztof talk, there are some things that we can say, at least like in the leakage resilience setting, about those, you know, those objects. But I don't want to talk about it right now. So all right, so that's bad. But arguably, at least, you know, PRGs we use, but at least PRFs and PRPs, nobody uses them directly. We usually use them to encrypt the data or authenticate the data. Authentication we already know is fine. So what about chosen plaintext secure encryption? Can I have this flip-flop behavior that the attacker is like completely right, he's like toying with us. On half of the keys he's right, on half of the keys he's wrong, so the square advantage is really horrible. So can it really happen? And this was like the very first surprise, so I promised some surprises. So this is like the first surprise of, this is really not one work, it's like, essentially what I'm doing is presenting 4 papers in one by just reordering presentations, so I can very comfortably present 4 papers of mine in one talk. But I view it as an advantage. So can this happen with CPA secure encryption? And I claim the answer is no. It contradicts CPA security. So here is a general lemma, which I'll prove on the next slide, that if the encryption is epsilon secure, again, is essentially, so I'm putting it as a symmetric encryption to quantify resources better. Again, it's essentially attackers with running time 2t+1 and 2q+1 queries. Then the encryption is square secure, where everything essentially drops by a factor of 2. Running time drops by a factor of 2, q drops by a factor of 2, and the square security is like epsilon over 2. So essentially ignoring those factors of 2, indeed for chosen plaintext secure encryption, the very first surprise already is that the square security is, roughly speaking, the security of the encryption. All right? So let's see why. So what's the magic here? So here is kind of the key observation why you know, you should love chosen plaintext secure encryption. The observation is it gives you ability kind of to test if you're right or wrong. And more specifically, the insight is that for any attacker that we care about in the real model, so red usually means real model, green means kind of ideal model, for any attacker making Q encryption queries, and who can potentially flip-flop and try to confuse us, be right on half of the keys and wrong on the other half of the keys, there exists another attacker making essentially twice as many queries, such as the advantage of the other attacker, even though it's smaller than the advantage of the original attacker, but it's always non-negative. It's the square of the advantage of the original attacker. Okay? So let's look at this attacker. It's a pretty simple attacker. So intuitively, here's what we are going to do. So first, before I play, so if Moni my own challenger, right, David is this kind of guy who tries to flip-flop for whatever reason, so I'm going to, but he's still kind of somewhat successful. So here's what I'm going to do. First, I'm going to kind of run David and see how good he is, and then I will check, but I'm not going to take the challenge from Moni. I will just, simulate Moni myself. I will just, David says I can distinguish encryptions of these two messages. I'll just pick one of those two messages myself, and I see if he's right or wrong. So essentially, and for that I need to spend Q+1 queries to Moni just to simulate the first attack. That's fine, but I'm not really playing with Moni yet. And then I see if he's correct. Then now I say, okay, so I know if intuitively if David has positive correlation with reality or negative correlation with reality. So now I run him again. Again is the real challenger against real Moni. Spend Q queries, and now David tells me his guess, and I should say, should I really trust his guess or not? And then I said, look, if he was wrong the first time, chances are that maybe he is confused. I'll just reverse his guess in the second time. If he was right, I say he's probably a good distinguisher, so I'm just going to take his guess directly. So intuitively, step 3 ensures that the advantage, at least on average, is kind of non-negative. And so this is kind of the attack, right? So the attack is clear. You just test once to see if he is right or wrong, and the second time, reverse the answer or not, depending whether he was right. And the analysis is pretty elementary. What is the probability that I win? Well, I win either if David wins twice, because the second time I'll take his thing which is correct, or if David lost twice, right? And those runs were completely independent. I just kind of ran David completely independently. So I don't know if his advantage epsilon was positive or negative in this run. It's plus minus epsilon, but whatever it is, if this is plus, this is minus. If this is minus, this is plus. So the overall probability of success, it's easy to see, is half plus 2 epsilon square. Okay, so a pretty elementary computation, and this kind of, intuitively it makes sense, right? And it's a really funny thing. That's kind of one of those funny things about probabilities. I'm not 100% sure that David is right, but by lots of probabilities, I know that overall, because I took into account one good run or bad run, I know that overall I kind of correlate David to reality in a correct way. So why is it enough for us? So now, of course, by definition, the square security, if I take the best attacker A, the square security sigma is expected value of advantage of A square, but that is 1/2 of advantage of B. But B is just a regular attacker, right? So because B is a regular attacker, this advantage is at most epsilon, right? So I indeed prove that sigma is at most epsilon over 2. Okay, so it's pretty simple. So now we have a really weird corollary of this thing. So the weird corollary is that if the encryption scheme is secure, essentially epsilon secure again is this attackers in the real model, then it is secure where I only lost a relatively insignificant factor of 2, but for the first time I get a useful bound, where yes, I lose a factor of 2 to the d, I lose a square root, but if you compare with the situation with the one-time pad, which was completely insecure, it's still actually, I don't want to say remarkable, but surprising that we got a decent bound, especially if d is small, right? So, and if you are curious, several people were curious, so I actually look it up. You can say, what if I run David 7 times and take majority of his runs, because the more I run him, the better confidence I get. And indeed, the analysis is a little bit messy, but Zvika Brajkerski and Odit Goldrich, as far as I know, without an application in mind, analyze something, not this particular problem, but they analyze something which essentially shows that if you want to save a factor of c, you need to run kind of c to the 4 times. This is kind of the trade-off. I'm not sure it will be that useful in practice, so I suggest running once is probably the best. For practical parameters is probably the best kind of trade-off. And the same argument, so this may be the second mild surprise, the same argument, I use encryption, but symmetric setting encryption and weak pseudorandom functions are almost the same. So weak pseudorandom functions are pseudorandom functions, but not on worst points, but on points which are random. It's pretty easy to see that this double run trick is just adverse for weak pseudorandom functions, so you immediately get a result of Krzysztof, but with different parameters and arguably much simpler proof, even though Krzysztof was essentially doing the same thing. He was just running the attacker many more times to get really high confidence. But I think for practical setting of parameters, it would be a much, the argument that the weak pseudorandom functions are secure even if the secret keys are weak I think you would get actually better parameters and shorter proof as in Krzysztof's paper. So yeah, but this is like pretty simple way to prove it. All right, so now maybe the next surprise. Let's keep going. Let's look at QI's independence, which you can view as some kind of bounded pseudo-random function if you wish. So what is almost QI's independent family of hash functions? So I have a family of hash functions, which is, there is this key R, which is our secret key, right, which is m bits, and it's a family of function from some n bits to l bits. And here I'll give you a slightly weird definition. It's weaker than the original definition, but it will be convenient for us. So here is a definition of QI's independence that I will use. So essentially, I will have Charlie and Alice, and I pick a random key for the hash function. And usually, in the definition of QI's independent, you want to say that any Q points the values of any Q distinct points look random. I will say, you know what? I want to say that the value of any point S looks random, even if the attacker can ask any Q minus 1 extra point. So essentially, I kind of send a challenge point to the attacker, right, to Alice. Alice just chooses any Q minus 1 distinct points, and then Alice learns the values of the function, the true value of our QI's independent hash function, those Q minus 1 points, and gets a challenge, either the real value of the point or truly random. And she has to distinguish it. So it's just a variant of QI's independent hash function. It's just I write it in this way because it's more convenient for me, right? So and then Alice just guesses real or random, right? So for example, t equals, so, and we can define naturally, given that we define it as in terms of game, we can define t q epsilon security and t q sigma square security of this primitive, right? For any particular hash function, given resources of the attacker, we can define those things. And now if the running time of the attacker is computationally unbounded and epsilon is 0, this is equivalent to standard QoS independent. It's pretty easy to see, perfectly equivalent to QoS independent. And now you can notice that we can run our double trick that we run for encryption. We can also run for this game as well. Why? Because essentially I'm just saying, first I can test. So if I get like a real challenge, so I get a real challenge from Moni, and David claims that he can kind of distinguish some kind of Q values from random, and Moni expects, like for me, is willing to give me 2Q minus 1 values. I get my challenge. Of course, I'm not allowed to ask the challenge to Moni, but then I choose my own challenge, and then, I ask it to David. He tells me which Q minus 1 points he wants in both runs, and I gave all 2Q minus 1 points to Moni. So essentially, sorry, maybe I'm confusing you, but essentially, I hope it should be pretty simple that I can essentially simulate this run, because in one run, using this 2Q minus 1 queries, I will just essentially get the points which are relevant in one run. In the second challenge, I just keep my challenge, and I can just do this, except there is one little subtlety. I have to make sure that my runs are legal, right? So I have to make sure that when I test David how good he is, right? So I ask Moni Q points which are relevant in one run. I want to make sure that those Q points are different from the challenge that Moni gives me, right? So there is this probability Q over 2 to the n that I might be unlucky. But because this challenge is truly random, this is fine, right? So does it kind of make sense, or did I guys lose you? So essentially what I'm saying is this definition, hopefully this definition is very natural. And essentially, I'm just saying, I want to prove that the square security of this application sigma q against QI's independence is at most epsilon 2q plus this kind of small error term if I'm unlucky. And the proof is exactly this double run that I made before, right? Because if not, I take any attack, I run him twice, and then reverse his answer if he is wrong. It's just there is a small probability that I could be unlucky, and the Q points that I use in one run, one of those points is equal to the challenge. Right, so does it make sense? So was it too fast? I mean, at least hopefully it's believable, but it's really the same proof, okay? So if you believe this thing, so I take silence as agreement, right? So but it's very natural, it's like nothing new is really happening. So now we can apply lemon 2, and now this is a surprise. So far we talked about QoS independence with completely random key. Now let's just apply lemma 2. Lemma 2 tells us that whatever the application is, if you can analyze that square security, you can simply take real key and replace it by the ideal key and see what you get, right? So let's just do it. And here is the lemma that you get. And the lemma that you get is the following, that if the family H is 2QIs independent, I mean this parameter epsilon, in the ideal model, this perfectly uniform key R, then you can argue that this family is TQ epsilon prime wise independent, so it's essentially Q independent, in the real model with the V key, where the security degradation is this 2 to the d under the square root times the square security. But I just proved to you that the square security is this, and this is epsilon, so this is a bound, right? So does it make sense? So this tells us, so essentially it tells us that if I pay a factor of 2 in the, how much independence I have in my function, I can get the real security of this function on half this Q. So let's see some special example in case it's abstract. So let's start with Q equals 1. For those of you who want to think ahead, Q equals 2 will be a surprise. But, Q equals 1, I claim that for Q equals 1, we get standard extractors. Or we get a different way to get standard extractors. So in this case, t is equal to infinity, epsilon is equal to 0. So and I want to rename my hash function like that, so I claim this is my definition. So I just copied the previous slide, I just renamed my function h sub r of s, I call it extractor, where the key is the source, and the random point is the seed. So just rename it extractor, and this is a game. There are no queries that Alice can ask because q is equal to 1. So q minus 1 is 0, so Alice cannot ask any queries. So what is the game? I challenge Alice on a random s, which is a seed for my extractor, and then I either tell her the extracted output, or I tell her a random string. So this is exactly, for those of you who don't know, if you don't know what extractor is, this is a definition. If you know, you will see that it's, our definition became the definition of extractor. So this is exactly the definition of extractor. So now you get the following very cute lemma, which I actually haven't seen before. It says that if you have a family of pairwise independent hash functions, right, then it gives you essentially an extractor. Well, it means it gives you this one wise independent hash function with a V key, which we just said it's an extractor, where epsilon prime is this bound 2 to the d minus n. Why is 2 to the d minus n? Because epsilon is 0, q is 1. So essentially it's just 2 to the d divided by 2 to the n, right? Because epsilon is 0 and q is 1. So it's just this bound. And if you just check, if you replace d by m minus d, you get this bound, which is...
it's not a different result than
we'll see.
leftover hash.
It's actually different results, so we'll see. I'll compare this leftover hash lemma on the next slide. But here is one interesting thing. So here I don't expect you guys to follow, just trust me, this is just for the reference. It's very well known what are the optimal keys for pairwise independent hash function. Turns out that the optimal key length turns out to be, usually we put like a factor of 2 to n, but it turns out you can do n plus l. You'll see the construction on the next slide. And if you plug it in, you get the bound. So if you plug in n plus l, you get that epsilon prime is the square root of the output length minus the original mean entropy, which is exactly the same bound as the leftover hash lemma, which is what Moni said. But it is not leftover hash lemma despite giving you the same bound. So let's actually compare it with leftover hash lemma. It was kind of cute because there are a lot of things which are kind of seem similar. So what is the leftover hash lemma? Just a reminder. So leftover hash lemma, it says that universal hash functions are good extractors. So what is a universal hash function? It's a function that I conveniently change indices that goes m bits to l bits with some seed s, and it has a property that for any two distinct inputs, the probability of collision is optimal. Essentially, if you hash any two inputs, the probability they collide is 1 over 2 to the m, right? Which is, turns out to be optimal, right? So this is universal hash function. Hopefully, people remember. And the leftover hash lemma, famous leftover hash lemma, says that universal hash functions define extractors, where the way they define extractors that the point is the source and the seed is the key for the hash function, keys of a universal hash function, with the same bounds that I put on the previous slide. So here we do something different. It's kind of funny. We use pairwise independence function, which is slightly stronger than universality, but we swap the key and the seed. So in our case, the source is the key for the function and the seed is the input. While for leftover hash lemma, the seed was the input and the source is the key. So as far as I know, there is some kind of coincidence here, and the coincidence is even more interesting because, as I said, one uses two-way independence, the other is universal. But if you look at the special case, if you look at the optimal universal hash function and optimal pairwise independent hash function, they collide actually. So this is one optimal construction. Ignore what is this k and so on. But essentially, if you just take your source, you split it into one more block, then you split the seed, and you take inner product plus rk plus 1, where inner product is over appropriate field. Over appropriate field. So if you look at this function, which is just canonical affine function, if you key it by s, if you key it by a slightly shorter guy, it's very easy to see that this is universal. If you key it by a slightly longer guy, it turns out to be pairwise independent. And you do get the same bound in both cases. So there is some funny collision, I'm not sure. But there's this kind of a different way to get the same result at leftover hash lemma, but as far as I can see, it's slightly different. Okay. All right. So I promised you the surprise. So let's look at q equals 2, and I claim we get something which really surprises. We get what we call non-malleable extractors in a stock paper with my student Daniel Wicks. But let's look at the primitive. As I said, we do the same thing except q equals to 2. What is the primitive? The primitive now is that I send, now R is already imperfect, so I have an imperfect source. I send the random seed to Alice. Alice is allowed to look at the seed and says, you know what, I want to see the output of extractor on arbitrary related seed S prime. So she kind of changes the seed in an arbitrary way. Then she gets the value of the extractor on S prime, and she has to distinguish the value of extractor on S from truly random. Right? So you can see there is some non-malleability going on, because you want to argue that the output, you know, even though she can learn the output of extractor on related seed, the output of extractor of the truly random original seed is still random, right? And luckily, you know, we already proved everything, right? We already proved that if our family H, which is used to define our extractor, is 4-wise independent, we get that H yield non-malleable extractor, right, for q equals 2, where, you know, you get this bound on epsilon, which is the same as before, it's just q equals to 2, so it's the same as it was before, but minus 1 because q is equal to 2. And now, as I said, I don't expect you to follow, but if you just look at a Lon Spencer book, what are the optimal 4-wise independent hash functions, so, you know, Moni's paper before that, it turns out that you can actually extract optimal number of bits. So if the key is of length m, you can actually extract m over 4 bits, which is optimal. And you can actually you can even push the input size up to half of the key size. In our notation, that's kind of the way to parameterize it. If you plug it in, long story short, you get epsilon prime is the square root of half of the output length minus mean entropy. Half of the input length, source length. So as long as mean entropy of our source is greater than a half, we get the entropy rate of our source is greater than a half, we get a useful bound. And indeed, you know, the barrier of half is essentially a barrier, you know, of non-malleable extractors. It was very recently improved to like 0.49999, but essentially a half is still a barrier. So this is essentially state-of-the-art construction. So we had this Fox paper last year with Lee, Woolley, and Zuckerman, where we use something much more complicated. We use like Paley graphs, and we use some techniques from Fourier analysis. And I think the paper was very well received and was invited as one of the top 7 papers to the special issue of Siam Journal of Computing. And in some sense, it's a bit embarrassing because this construction hands-off beats the construction from the Fox paper. Even though the entropy rate is the same, the actual bound is better. There we had to use some unproven conjectures in number theory. We could only extract like 1 bit. For more bits, it was kind of messy. So this kind of is a strictly better construction. But of course, I'm glad that we didn't come up with a simple construction, because if we did, it wouldn't be invited for the, you know, to the Siam Journal of Computing. Because if people see like one-page proof, they will be unhappy. So, and I'm just joking. But anyway, so this is kind of cute. And if you want to see, just so that you are like, you know, what is the particular construction? If you think it's something complicated, it's actually very, very simple construction. So this is a construction. So you take your source, you split it into 4 equal pieces. You take your seed, which is actually half as long as the source. So it's not even that bad. You just take the seed, you cube it, okay? And you exclude seed equals to 0, let's say. So you cube it. After you cube it, you just split S and S cube into 4 pieces, right? You cube it in an appropriate finite field, and then you just output the inner product. So this is, it's you know, a classical result using BCH code that this is a 4-wise independent hash function. But you know, the non-malleable extractor is actually pretty simple. Right? It's 4-wise independent because for any S, it's easy to see that any 4 vectors will be kind of linearly independent. And the unfortunate thing, it was kind of funny. My co-author told me that he has another paper on non-malleable extractor, which I didn't look. He came up independently with the same construction with a totally different analysis, but also actually a very funny collision, because we arrived through this analysis using also some totally different techniques. Okay, so I'm actually done with the dumb technique. So I hope I convinced you that by being pedantic and just following some pretty simple rules, at the end we got some pretty surprising and powerful results, which were considered open problem for like 3 years and so on. So you know, there is some point of just you know, following one particular path. But let's actually try to be even smarter. Let's try to go from the dumb approach to key derivation approach, right? So when you go to key derivation, so far we just use a key directly, and still we got surprisingly powerful bounds. And the funny thing is, we didn't try to be smart, right? We just use a key down in a dumb way, and we still got extractors. So it's kind of in an ironic way. We didn't try to actually derive a key, but in some indirect ways we got extractors. But now what we actually really try to design a key derivation function. So now we have a source of length n, let's say much bigger than the output length that we want. Like m is, let's say, 128 bits. And we try to define a good extractor, which is good for our application. So there are kind of two options. So the options that have been used before kind of our work from last year, the work with Bas and Krzysztof, which I'll mention in a second, essentially the option was, well, the best way to do this modularity is to design an extractor. And I already told you how to design an extractor. And then once you design an extractor, R is statistically close to uniform, you can just use R. That would be a good approach. So it works, but in some sense we'll see that maybe it's an overkill. It kind of ignores security of P. So I said, look, we are trying to be pedantic and not to jump to conclusions, so let's try to be pedantic. Let's use lemmas 1 and 2. We have those cool lemmas 1 and 2, right, that we designed that were super general. And let's just see what property of H is needed. If H is an extractor, we'll use an extractor. If H is something else, we'll use something else. And then, we'll see which property of H are needed so that the derived key satisfies the precondition of lemmas 1 and 2. All right? So let's revisit our lemmas. Actually, lately I like to title all my papers like something revisited. So we have like leftover hash lemma revisited, message authentication revisited. I don't have a papers lemma revisited, but I named the slide lemma not yet. So actually, no, I just submitted a paper which called Shannon Impossibility Revisited. So I'm looking for more suggestions how to name papers revisited. So anyway, so this is our setting. Remember, so we have a secret X. It says length n. It has entropy k. And we want to derive an m-bit secret. And this is what lemmas 1 and 2 told us, right? So lemmas 1 and 2 told us that if the entropy of R is like m minus d, there are different notions of entropy here, then you get this, this kind of degradation. So now let's just put our glasses. I already have my glasses on, and let's just do pattern matching. So it says, okay, this is what is known about X. This is what we need to apply lemmas 1 and 2. And it seems like it's a pretty natural. It's not exactly an extractor. It's an object that is called a condenser. And depending on, so let's say C is like either 2 in infinity, because we'll see it, in one lemma we want to get infinity in the other 2. That's why I didn't put entropy here. But it's actually a pretty natural object. I will say that the function H is a condenser with appropriate parameters if, as long as the mean entropy of the input, or not mean entropy, but whatever, mean or any entropy of the input is k, then the mean or any entropy of H of X is m minus d. Right? So if I get this thing, you can see that things match up, right? Right? So if I can define a condenser, I know that I can exactly use my things. So intuitively, what does a condenser do? It goes from entropy rate k over n to entropy rate m minus d over m, where hopefully d is as little as possible. So extractors kind of insist on d equals 0, but we say, look, even if d is not 0, we'll still get maybe decent results. So let's not be paranoid and insist on d equals 0 necessarily, right? And one question is, what is non-triviality of extractor? If you think about it, the non-triviality of the extractor is that the entropy deficiency of the output, which is d, should be significantly, hopefully, but much less than the entropy deficiency of the input, because otherwise you can just truncate the input and get some trivial condenser. So this turns out to be non-triviality. So in some sense, you can view as a condenser as a way to kind of hunt down good bits, but maybe not necessarily with good probability, but just kind of identify some good bits and maybe copy some of the bad bits, but at least get some of the random bits. All right, so one small subtlety. So far I just define a condenser as a deterministic function, but it turns out, just like extractors, for those of you who know, and those of you who don't, I had a slide defining extractors before. Extractors need seeds, so condensers also need seeds, because otherwise, if a condenser is a deterministic function, you can have some artificial distribution, which is, let's say, all pre-images of 9 or something like that. Right, so this distribution has really high entropy, but obviously if you apply H, you get a constant. So you get something like that. You would get a key derivation function that keeps outputting 9 all the time. So we want to kind of avoid these cases. And now, of course, there is this kind of key question for condensers, which we can ask. And the question is, the seed S should be public, right? Because, X is the only secret we have. The seed S is public. So the question is, can the distribution of our source X depend on the seed or not, right? And no matter how you answer, you're stuck with one of the papers that we wrote. So if the answer is no, which is a traditional setting, namely we assume that the adversary doesn't have enough power to control the distribution of x, to make x dependent on s, so s maybe is chosen afterwards, you get this crypto paper joined with both Krzysztof and friends. And otherwise, you'll get our TCC paper, but as we'll see, they will be very similar. I'll cover both in one slide, well, in 2 slides maybe. So this is a TCC paper which we just presented with Tom Riesenberg and Salil Wadan. But in both cases, before I get into these details, this is something that very interesting which happened in both cases. Remember, we had these 2 flavors of condensers: mean entropy condensers and Renyi entropy condensers. But in both cases, the way we the only way we know, I mean, it's not a theorem, but the only way we know how to obtain mean entropy condensers was first that we obtain Renyi entropy condensers, which happen to be kind of a more natural object in some sense, and then use some general properties of entropy to convert them to mean entropy condensers. But what we do is we then kind of start here, go to H infinity and apply lemma 1, we get same or worse bounds than if you just get H2 condensers directly and then apply lemma 2. So even for predictability applications, so for indistinguishability applications, applying lemma 1 is not an option, right? Lemma 1 was only for non-negative f, but for unpredictability applications, we have these 2 options to go, but in both cases, lemma 2 was useful, because in both cases, in order to construct H infinity condensers, we had to go through H2 condensers. So essentially, what I'm going to do with surprising is, I'm going to construct condensers for any entropy, all right? And let's start with the seed-independent condensers. So what is a seed-independent condenser? Let's recap our setting. So our setting is the following. I know that the collision probability of my source is 2 to the minus k, and I want to conclude that the collision probability of h of x, even condition on the seed, is 2 to the d minus m, right? So it means that the collision entropy of the output is 2 to the d minus m, right? Because remember, we need seed, so we need to condition on the seed, right? So is the question kind of natural? So I want to design some kind of shrinking function that preserves collision probability, and this is exactly what LHL, so this is really LHL. This is essentially what half of the analysis of leftover hash lemma does, and then the second half of the analysis talks about how to achieve d equals to 0, but we are going to stop at the first half. And essentially here is a lemma that if you have a universal hash family from n bits to m bits, they define a condenser, from k over n to m minus d, in a natural way where you just, the seed is the key for the function, the source is x, where 2 to the d, remember 2 to the d is the quantity that we care about, so 2 to the d is this kind of quantity. And so what is this quantity? It's 1 plus 2 to the output length minus the entropy of the input. So in typical settings where the entropy of the input is much higher than m, this is essentially 1. So this is a fantastic result, and not surprisingly, indeed, that's why in this setting, we can even obtain extractors. We can even obtain d equals to 0. But let's just prove this lemma. The proof is 1 line. That's the whole proof. So I need to analyze what is the collision probability of when I apply my condenser twice on independent sources, right? So if I pick independent x1 and x2 and just pick a random s, what is the probability that they collide? Well, there are 2 cases. Either I'm unlucky and x collides already. So definitely, if x collides already, I lost. I mean, there is a collision. Or x is not equal, but then I was still unlucky and those guys collided. So the first probability by definition is exactly the collision probability of my input, right? Right, because this is exactly how collision probability is defined. And the second probability, if I know that x1 is not equal to x2 and I choose a random key for the universal hash function, by definition the probability is 2 to the minus m. The collision probability is 2 to the minus m. So, and now if you want to get this bound, remember, if I want to get 2 to the d, I care about 2 to the d, I take my collision probability and I need to multiply it by 2 to the m. So if I take this number, multiply it by 2 to the m, I get exactly what I want. I mean, what I get there. And now essentially this is n. And now we can apply lemma 2, but the bound we got was so remarkably strong in this case that it turns out it's actually more convenient to get a refinement of lemma 2, which is essentially has the same proof, but the only difference exactly the same as before, but I don't upper bound the expected value of f. I upper bound the expected value of f minus expected value of f under uniform distribution. And what I gain is this seemingly insignificant one. So in most cases, it's kind of, the bounds, we are so happy to get any bound at all. This minus 1 is not helping us. But here the bound is so fantastic that I get a really good result, and namely the result that I get in this case is the following, right? So now we are kind of back, to our application to key derivations. That if I have an application which is epsilon secure, this is our epsilon, this is our sigma, right? And t sigma square secure, then if I derive a key using a universal hash function, then I get that the application is t epsilon prime secure in the real model, where epsilon prime, this is epsilon prime, is at most epsilon plus sigma, and when I subtract 1 from this bound, I get 2 to the m minus k, right? So now, if the bound looks weird, let's actually compare it with leftover hash lemma. So I claim that by being pedantic, we actually get results which are better than the ones that we can get by just deriving a key in a pedantic way, deriving a key using an extractor. So let's define the entropy loss as a difference between the entropy that we have and the output length, right? So I have a source of entropy k, I derive m bits, so it means that I lost kind of L bits from my entropy. So now, the standard leftover hash lemma, which I kind of prove, if you translate it to this setting, right, previously we had exactly this m minus k, so it means that epsilon prime is at most epsilon plus, so, right, it means that new security is original security plus statistical distance from uniform. And this is 2 to the minus L. Right, so in particular, if you want to get a comparable level of security, if you want to get epsilon prime like 2 epsilon, so it kind of says, you know what, I derived a key and I didn't lose that much, it means that the entropy loss is essentially 2 times security parameter. It's like 2 log 1 over epsilon. Right, so I have to lose, let's say, 160 bits if I want security parameter 80. So and also, it's not meaningful if I have negative entropy loss. Irrespective, even if I have a super secure 2 to the minus million secure application, if somehow I'm forced to, to have entropy loss 0, the leftover hash lemma doesn't give us anything useful. So in our improved bound from last crypto paper, which, as I said, is epsilon prime is epsilon plus there is an extra sigma under the square root. So now, for many applications, recall in the first part of the talk, I argued that the square security is essentially regular security. So for all these kind of applications, CPA encryption, weak PRFs, QoS independent hash functions, we get that epsilon prime is at most epsilon plus this kind of bound. So essentially, there is an extra epsilon under the square root. So in particular, it suffices to have L greater or equals than log 1 of epsilon for comparable security. But not only that, there is another surprise. We start to get useful results when we extract more bits than the amount of entropy we have. You see, how can we get useful results? Well, we borrow the security from our application. Because if our application was super secure, we didn't suddenly lose security just because we extracted 1 more bit than the entropy we have. So the security kind of gracefully degrades. So for example, for entropy loss 0, we still get, respectable security square root of epsilon. All right, so by being pedantic, we kind of got pretty surprising result of kind of improving classical LHL. And the final technical thing in the last kind of slide is, what about I promised to cover our TCC paper in 1 slide. I'll cover half of our TCC paper in 1 slide, not counting, of course, all those other slides. So now, what is our goal? So our goal is now actually very, very ambitious. And until we wrote the result, I couldn't believe we can actually get something. So this is a setting which, if somebody told me half a year ago or whatever, before we wrote the paper, I wouldn't expect anything can be done. Extremely adversarial setting. So I have the source X, and the source X it could depend on the seed. So there is this, seed for the function. This function H is public, and somebody can come up with adversarial distribution X, which still has collision probability. And what I want to argue is that the collision probability of H of X given H is low. And here, unfortunately, it looks impossible because it is impossible. The same example as before works. I mean, if X could depend on H, I can still kind of, it doesn't matter that H was chosen at random. You choose it, you fix it. You can still sample X to be H inverse of 9, and then, of course, you're not going to get any entropy here. So what we notice here, why doesn't this result impact practice? Well, because in practice, we cannot invert arbitrary crazy hash functions. So if the hash function H is kind of cryptographically strong, for example, if it's efficiently sampleable given H, and we use a cryptographically strong H, it's not clear that this attack works. Of course, it doesn't mean that the application is secure, but now, for the first time, we get a hope to get it. And indeed, if we talk about extractors or condensers for efficiently sampleable sources, they were considered by Trevisan and Vadan in 2000, but unfortunately, they were insisting on getting extractors, and extractors are just too good, it's kind of much harder objects than condensers because D is equal to 0, And in this case, it's very easy to see that the sampler who samples this adversarial distribution X, you cannot allow the sampler to run the extractor, because then essentially the attack is the following. If the sampler can run the extractor, I can say pick random X. If the first bit of the extractor is 0, output X. If not, pick it again. So in 2 trials, you will kind of effectively fix the first bit of the extractor to 0. So they couldn't do it, and therefore it's kind of in practice it wasn't very useful, because if H is like SHA, it means that all the sources which are sampleable in time faster than the running time of SHA, which is not a very useful set of sources. But in our case, we kind of observed, look, the best generic attack seems to be exactly what I told you. So if the sampler can kind of run T copies of the extractor kind of T times, I cannot think of a better attack. Maybe it exists, but the best attack seems to be kind of to fix the first log or whatever, some log T bits output of the condenser, but just keep sampling X until you fix the first log T bits to something. At least I cannot think of a better attack. And in this case, it's not so bad. If D is log T, 2 to the D is T, so yeah, we lost like polynomial factor in security, but it doesn't kill us completely. And indeed, the surprising theorem with a surprisingly simple one-line proof, and that's the last thing that I'll do in the last 2 minutes, is that strong enough collision-resistant hash functions are good condensers. So, and the reason I like this theorem a lot, it kind of partially explains the use of cryptographic hash functions for key derivation. Because there, nobody, SHA has a fixed seed, and everybody still uses SHA. So why isn't there a theoretical contradiction? Because look, in practice, nobody is going to give you some kind of source X that will fix the output of SHA to 0. I mean, otherwise you can find collisions intuitively. And this theorem exactly formalizes the thing in a precise quantitative way. So you kind of follow the exact security approach. And this is essentially the theorem. The theorem is very simple, and the proof is very simple, and we'll get the parameters from the proof. Essentially, the theorem is, look, I have to argue that if H is collision-resistant hash function, the probability of collision is very, very small if I sample x1 and x2 twice, independently, but conditional on H. Well, why? It's the same analysis before. Look, if I'm unlucky and x1 is equal to x2, it's too bad, but that happens with probability 2 to the minus k. That's a requirement on our sampler. But if they're not equal, what is the chance that if I sample twice using an efficient sampler, 2 independent x1 and x2, what is the chance that x1 is different from x2, but the hashes is the same? Well, it better be at most collision resistant of SHA-1, because otherwise, I broke SHA-1 using a pretty trivial kind of attack, sample 2 random guys and just hope that they collide. So this is definitely at most a collision resistant of SHA. And as a result, so just trust the parameters. I know it's late in the talk, but essentially, if you just assume that SHA is a very, very good collision resistant hash function. So if it's the best probability of collision is some kind of A of t in time t, if the best probability of collision is A of t times 2 to the m, essentially you get this bound on 2 to the d. So now if this is 2 to the d, it's 2 to the m minus k, which is a good, it's like a tiny number if k is greater than m, but you do have to pay this A of t. So if you look at the best bound on collision resistant hash functions, which is t squared divided by 2 to the m, so we assume that the only way to find collisions is by generic attacks, then A of t is t squared, and then essentially in this case, this is a dominant term, we get that 2 to the d is t squared. So we constructed a condenser such that 2 to the d, 2 to the entropy deficiency of condenser, is at most t squared, where t is the running time of the sampler. So now, if you just put this theorem, here is a corollary. So in case you lost me with some technical things, the immediate corollary is kind of the following, that if H is, let's say, optimally collision resistant, but of course you can get bounds even in the non-optimal case, then the real security epsilon prime you get if you derive the key by just hashing the input, right? Hashing the input using collision resistant hash function is at most square root of sigma times t, where t, because it was square root of t squared, so square root of t squared is t. So essentially, asymptotically, and this is true against any source x, which can be sampled even adversarially after the hash function is fixed, after the fixed IV for SHA, right? After the hash function is fixed, as long as the source must have some kind of non-trivial amount of entropy. So the asymptotic view, we kind of go back from exact security for a second asymptotically. If we start with the negligible ideal security, remember sigma is at most epsilon, roughly speaking, and you have polynomial adversarial sampling time t, you still end up with much worse, but still negligible security. So it's like polynomial times negative. So I mean, yes, the degradation is pretty horrible. In practice, you are not going to be happy with this result. But this is a remarkably adversarial statement. I'm saying even if somebody tries to come up with some source, that you will just apply SHA to, the best they can, and they try to, the source has to have entropy. After you hash the source, the output still has non-trivial amount of entropy. Anyway, so I think it's actually perfect 1 hour, depending when I started. So I think it's my conclusion slide. So I think I kind of demonstrated you. Maybe I gave too much information, but I tried to put 4 talks into 1 talk. So once 1/4 of an hour, it's not bad for a paper, right? Kind of on average, in an amortized sense. So hopefully you'll kind of agree that I gave you some surprisingly simple yet powerful techniques to deal with weak randomness. And connecting to my first slide, hopefully the techniques are kind of neat, and the applications were kind of fun and somewhat surprising, especially towards the end. Some particular thing, I think this application motivated the study of square security. In particular, this very simple double trick handles important indistinguishability applications. And in some sense, I think this way of kind of pedantically presenting results, I think it helps simplifying, unifying, sometimes improving prior results, encryption with weak secrets like leakage resilient encryption, non-malleable extractors, you have the entropy loss of leftover hash lemma, seed-dependent condensers. So if I just put these applications kind of in one bullet, you would think there is no connections, like completely insanely different. I mean, yes, they're kind of about cryptography from weak secrets, but completely kind of different objects. So it was kind of surprising that things kind of collided. And of course, I'm hoping that there will be more applications of this kind of technique, so maybe future techniques. So that's all I have to say.
You have questions?
So I didn't understand what you said about higher moments. So do you know if like Q security or something like that?
Oh no, so for QoS independence, you mean, or?
In general, if you have applications of.
So there are 2 ways to interpret your question. I'm not sure which one you meant, but for different Q, you can talk about QoS independent hash function. That corresponds to a flavor of non-malleable extractors where you can ask the value of the extractor on Q different seeds, and everything works. Yeah, you get essentially very good bounds even in this case. Essentially the same bounds that I showed kind of gracefully degrade. So this is one value. The other value, maybe you're asking if instead of Cauchy-Schwarz, you use Hölder's inequality. So in this case, we thought about it, but unfortunately, when you use Hölder inequality, it's like 1 over P plus 1 over Q equals 1. So if one of the guys is an integer, the other guy is not. So maybe it's just, I thought about it, and several people actually asked me. I couldn't find something minimal, but on the other hand, I think there should be something meaningful. It's just maybe we didn't think about it enough, and maybe it gives you some surprising trade-offs. So my guess is the answer is yes, but the most obvious thing that we spent like 10-15 minutes somehow didn't seem to work.
Questions? Let's thank the speaker again.